Okay, welcome back. And today we're going to go into more about probability. This title's wrong, but it's going to be um, basic concepts in probability. So last time we introduced probability, but now we're going to talk about basic concepts. So one of the things that I mentioned earlier when we were talking about the union rule for sets, I said this is going to come back, and here it is. This is the union rule for probability, or what I call the addition rule for probability, and it always works with or statements. So when you take the union of two sets, so we're finding the probability that event E occurs or F occurs. So this is E or F. So the probability that either E occurs or F occurs or both. And so we're going to use the union rule, or what I call the the general addition rule. Okay. So what you do is very similar to what we did when we were adding the numbers of objects in a particular set. So we're going to take the probability of E plus the probability of F minus the probability of both E and F occurring. And so this should be very straightforward and easy to understand if you just remember the definition of probability. The number of outcomes in E divided by the total number of outcomes in the sample space, plus this is going to be the total number of outcomes that give F over the total number of outcomes in the sample space, minus the total number of outcomes that give us this divided by the total number of outcomes in the sample space. So what you get is actually adding all of these together, adding these two together and subtracting all of this and dividing by the total number of outcomes in the sample space because they're all the same. Okay, so this is like adding fractions with a common denominator. Okay, so it's really directly related to what we were dealing with sets because that's exactly how we defined probability, right? Now, if we have this, it says, if a single card is drawn from an ordinary deck of cards, find the probability of an ace or a club. Now, if you think about it, you can figure this out without applying the rule directly, right? I mean, you could apply the rule in your head, right? You could say, okay, well, are they mutually exclusive, right? Can I get an ace and a club at the same time? Well, no, because aces and clubs are disjoint. You can't have an ace, or excuse me, I'm sorry. I'm brain dead. Yes, you can have an ace and a club at the same time. You can have an ace, the ace of clubs. Okay, so you can have an ace of clubs, right? So we're going to be adding something twice, right? Because we can have an ace and a club at the same time. There's one card, the ace of clubs, that can happen where we get both an ace and a club. So remember what we're going to do. So to do ace or a club, we're going to count up all the aces. How many aces are there in the deck? 4. How many clubs are there in the deck? Right? We're going to use our rule of unions, right? So how many aces are in the deck? 4. How many clubs are in the deck? 13. 4 plus 13 is 17. But remember, we got to subtract off 1 for the intersection because we're counting the ace of clubs twice. Okay, so we're going to subtract off 1 for the ace of clubs, and so we're going to get 16. So the answer is going to be 16 divided by the total number of possible outcomes, which in this case is a 52 cards in a deck. So it's going to be 52 different possible outcomes. So it's going to be 16 out of 52, or 8/26, or 4/13. Okay, but if we apply the addition rule, we get the same answer. So let A represent the event of getting an ace. Let C represent the event of getting a club card, a club. And so there are 4 aces in a deck, so the probability of getting an ace is 4 out of 52. there are 13 clubs in a deck, so the probability of getting a club is 13 out of 52. Since there is one ace of clubs in the deck, the probability of getting an ace and a club is 1 out of 52. And so now if we use our union rule or the addition rule for this probability, then we will get the probability of getting an ace or a club is going to be the probability of getting an ace plus the probability of getting a club minus the probability of getting the ace of clubs, which is 4 plus 13 minus 1, which gives us 16/52, or 4/13, which is what we came up with. Okay, now suppose we have two fair dice that we're rolling. So we roll two fair dice. Find the probability that the sum is 8, or both die show the same number. So this is either or. Okay, so now if we think about it, how many different ways can I get 8? Well, let's see, so I can get a 2 and a 6, right? I can get a 2 and a 6. So if I look at the dice as dice 1 and dice 2, die 1 and die 1 and die 2, I can get a 2 and a 6. I can get a 3 and a 5. I can get a 4 and a 4. I can get a 5 and a 3. I could get a 6 and a 2. Okay? So there's 5 ways of getting an 8. Now, how many different ways can I get a roll where both die have the same number? Well, I can get a 1 and a 1, 2 and a 2, 3 and a 3, 4 and a 4, 5 and a 5, and a 6 and a 6. So we get a total of 5 or 6 outcomes for that one. Okay. Now, is there a way to get both an 8 and have the same number show up on both die? And the answer is yes. I can get a 4 and a 4. So there's one way where both will happen. So if I use the rule, I'm going to add up the number of ways, right? I can get an 8, that's 5, plus the number of ways I can get the same number on both die, that's 6, so that gives me 11. Then minus the one way I can get both, so that gives me 10. So, and how many possible outcomes are there on rolling 2 dice? Well, there are 36 possible outcomes. So in this case, it's going to be 10 out of 36, or 5/18. Okay, but let's set it up. Okay, so here are all possible outcomes, right? So I can do 1, 1, 1, 2, 1, 3, 1, 4, and so on. So the first number is the first die. Second number is the result on the second die. So these are all of the possible outcomes. Okay. Now I want the probability that the sum of the 2 dice is 8, or I get the same number on both die. Okay. So I want that probability. So how many different ways can I get a sum of 8? Well, where are they? They're right here. Oh, where are they? Oh, right here. These 5 right here. Okay. And how many different ways can I get the same number on both die? Right here. This diagonal right here. Notice that they both intersect. Get it? And intersection. Both of these events intersect. There's overlap. Okay. So in this case here, again, if we apply the rule, we get 5/36. 5 out of 36 is the probability of getting an 8. 6 out of 36 is the probability of getting the same number on both die. And then here's the probability of getting a 4, 4, which is both. The same number of both die and a sum of 8. And then I get 10/36, which is 5/18. Okay. Now in this case here, what are they saying? Well, what is the probability of event A A is getting a 2 on the first die, or getting a let's see, getting a 6 or 7. Okay, so I want the probability of getting either a 2 on the first die or getting a 6 or a 7. Well, how many different ways can I get a 2 on the first die? Event A. Well, so I want the probability of A or B. Well, what's the probability of A or B? Well, it's how many different ways I can get A, plus how many different ways can I get B, minus the probability of A and B. Okay, so what's the probability of getting A? That's going to be 6 out of 36. How many different ways can I get B? That's going to be what? That's going to be 10. No, that's going to be 11 out of 36. And how many? What's the probability of getting both? That's 2 out of 36. So if I add this, so I get 11 plus 6, which is 17, minus 2, which is 15, I get 15 out of 36. Or 5/12. Okay. Or what if I say, what's the probability of getting A and B? Well, how many different ways can I get both? Well, I kind of already figured that one out in the last problem, right? It's going to be 2 out of 36, or 1/18. Okay, see how this works? Now, the next rule is the complement rule. The complement rule is comes directly from the fact that all of the probabilities in an event, all of the probabilities in a sample space must add up to 1. Okay, the sample space, the probability of the sample space must be 1. So if I have all of these events in a sample space, well, the probability of each outcome is going to be a number between 0 and 1, remember? So also, to be a valid probability, all of the probabilities must add up to 1. So the complement rule happens when you only have, let's say you define an event. For example, let's say I define an event that a randomly selected tire will last more than 40,000 miles. Well, in that event, I could say, okay, either a randomly selected tire is going to last over 40,000 miles or it's not, right? There's only 2 outcomes, right? Either, if I reach into a bag of M&Ms, either I'm going to pick a green M&M or I'm not. Or if I flip a coin, I'm either going to get a heads or I'm not. If I have a randomly selected baby that was just born, well, the baby's either going to be male or female. So in all of those examples, we have an event, and either the event is going to occur or the event does not occur. And this is where the complement rule comes in, because if we take the event that something occurs, and we take the event that it doesn't occur, the probabilities of those 2 events must add up to 1, right? Okay. So in this case, this is where the complement rule comes in, because I am just solving for one of the 2 events, right? Because this event plus this event must add up to 1. So I can write the complement rule as the probability of an event is equal to 1 minus the probability of the complement. Or the complement is equal to the probability of the probability of the complement E prime is equal to 1 minus the probability of the event, which is also the complement. So again, it works either way. So it says find the probability that when 2 paired dice are rolled, the sum is less than 11. Well, I can add up all of the probabilities, right? So the probability that the sum is less than 11, okay, right? Or what I can do is I can say, well, how many outcomes are equal to or greater than 11? Well, there's 3, right? Because to get an 11, I can get a 5 and a 6 or a 6 and a 5. And to get 12, there's only one way to get 12. That's 6 and a 6. So there's 3 out of 36 possible outcomes, right? So I can start with that. So I know the probability of getting 11 or more is 3 out of 36, right? So I can use the complement rule to answer this question and say, well, if I know that the probability of getting 11 or 12, right, is 3 out of 36, then the probability of getting less than 11 is going to be 1 minus the probability of getting an 11 or 12. So it's going to be 1 minus 3 out of 36, which is going to be what? 33 out of 36, or 11 eighteenths. Okay? And so there's where we go. So we can calculate this probability directly, because all we have to do is find the probabilities of that the sum is 2, 3, 4, 5, 6, 7, 8, 9, or 10. Right? So we can add up all these probabilities. The probability of 2, the probability of 3, the probability of 4, right? So the probability of 2 is 1, right? 1 out of 36. This is 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, 5 out of 36, 4 out of 36, and then 3 out of 36. And so we can add up all of those probabilities and get the same answer. Okay, or we can use the complement rule, because either it's going to be less than 11 or it's not, right? So I can split this up into 2 different sets. This is set A and this is set B, right? So I can find this one easier, right? This is the smaller one, much smaller. So I know this probability is going to be 2 out of 36 plus 1 out of 36, or just 3 out of 36. So there are 3 outcomes that are above 10, okay, or equal to 11 or 12, okay? So then to find the complement, all I have to do is 1 minus 3 out of 36, which gives me the same answer, okay? And so the probability that the sum is less than 11 is equal to 1 minus the probability that the sum is greater than 11. And so we get 1 minus 3 out of 36, which is 33 out of 36, or 11 twelfths. Okay, and there's our answer. Okay, now odds. Odds we hear a lot in Vegas, gambling. So what's the odds? The odds, and we're going to talk about specifically the odds in favor. There's odds in favor and odds against, right? So the odds against is just the reciprocal of this, but we're not going to talk about that. So the odds in favor is we just take the probability of an event occurring divided by the probability of the event not occurring. Okay? And so when we apply the definition of probability, it really becomes the number of outcomes that give me the event divided by the number of outcomes that don't give me the event. Okay? Because the sample space cancels. Okay? And again, the probability here cannot be 0. Okay? We're assuming that that's not going to be 0. Okay? Because if this was 0, hypothetically, it's a certain event, and it's definitely going to happen. But anyway, we don't deal with this, so we don't want to divide by 0. Okay, so this is the way we define odds. Probability of an event occurring divided by the probability that it won't occur. And so if the probability of snow tomorrow is 3/10, find the odds in favor of snow tomorrow. Well, if the probability of snow tomorrow is 3/10, what's the probability of that it doesn't snow tomorrow? 7/10, right? Because it's a complement. They're complements of each other, right? So either it's going to snow or it won't snow. So if I was to write this as a odd, if I was going to write this as odds, to give the odds, then it's going to be the probability of it snowing, which is 3/10, divided by the probability that it doesn't snow, which is 7/10. Well, the denominators cancel, and we end up with 3 over what? 3 over 7. So it's a 3 to 7 odds in favor of it snowing. Okay, and there's the solution. Okay, and this is, this is, be careful with the S. Usually we use S for the sample space, but just make sure it makes sense if you read the context. Okay. Okay, so the odds is 3 to 7 that it'll snow. Now, if you're looking for a probability and you've gotten the odds, let's say you've got the odds. Okay. Well, if you want to use the odds to help you find the probability of an event occurring or its complement, then this is the formula for probability of the event happening. It's the odds, right? So here are the odds. If the odds in favor of E are m to n, so number of times that it will occur to the number of times it won't occur, okay, then the probability of the event occurring is going to be the number of times it occurs plus the total number of outcomes, right? It's going to be the number of times it occurs plus the number of times it doesn't occur, right? So this is going to give us our denominator, right? So it's going to be m over the total. The probability that it doesn't occur is just the n, right? We're going to, instead of m, it's going to be the ratio. So basically relative frequency, right? The number of times that it occurs over the total number of outcomes, or the number of times it occurs over the sample size, okay? So here we get m over n plus m, and the probability of it doesn't occur is now we're just going to replace it with n. So now, in this case here, it says if the odds that a package will be delivered on time are 17 to 3, find the probability that the package will not be delivered on time. So that means, in this case, we want the number of times that it will not be delivered on time on top in the numerator. So that means the 3 is what's going to be on the numerator, because this is the odds in favor of it being delivered on time. So this means that 17 times it will be delivered on time, 3 times it won't. So this is going to be 3 divided by the total, which is 20. So it's going to be 3 out of 20. So 3/20 is the probability. Okay. Or if you write it as a decimal, it'll be, let's say 3/20. 0.15. So it'll be 0.15 is the probability, or 3/20. Okay. Or that it won't be delivered on time. So the probability that it won't be delivered on time is 3/20. Well, guess what? Then the probability of that it is delivered on time is 17/20. Okay. So here are the properties of probability. Okay. Remember these. So now, if we have a sample space that consists of n distinct outcomes, right? So we have S sub 1 over S sub n, or 2 S sub n. So we have n distinct outcomes. These would be the simple outcomes, simple events, right? So these are the n possible distinct outcomes, right? An acceptable probability assignment consists of assigning each outcome, S sub I, with a particular probability. according to these rules. Now, if it is a valid probability experiment, then these must hold. So that means each probability of each event, each outcome in the sample space must have a probability that's between 0 and 1, which means no negative probabilities and no individual probability can be greater than 1. Okay? And number 2, the sum of all of the probabilities in the sample space, of all, the probabilities of each event in the sample space must add up to 1. Those two conditions must hold. Okay, so let's look at consumer credit. So we have the holder, so these are the different institutions, right? And so we look at the amount of, as far as the different institutions, right? And these are the amounts that they hold at each one of these different financial institutions, okay, as far as consumer credit, the amount of loans that they hold, okay? So these are depository institutions, so these are banks, finance companies, credit unions, federal government, non-financial business, and pools of securitized assets. Pools of securitized assets. Okay, I'm not sure what those are. Are those homes? Not sure. Are those mortgages? Not sure. But anyway, so now what we want to do is we want to change this into a probability distribution, a probability table, PDF. So what do is we add up all of these amounts to a total. And so we're going to use the relative frequency definition of probability. We're going to add up all of these numbers and get a sample size. And then we're going to divide each of these individual numbers by that total. And that's going to give us a probability for each of these events. The event that a randomly selected person will have their credit held by any one of these particular institutions. So if we do that, you will get these probabilities. Now, one of the things, remember, check to see, make sure that it meets those two conditions. So by glancing at this, we see that we don't have any probabilities that are bigger than 1, and we do not have any negative probabilities. The other thing we have to check is to make sure that these add up to 1, or very, very close to 1. So if we add these up, we get 0.6, 0.7, we get 0.81, 0.89, 0.93, 0.97, 0.98, 0.99, 0.998, 0.9988, and 0.9999, and we get 0.9999, which is close enough to 1. And so we have a valid probability distribution. Okay, now we can answer questions about probability. Now I can say, okay, what's the probability that a randomly selected person is going to have loans with either credit unions or finance companies? Well, the way we find that is we're going to use our rule, right? So what's the probability that a randomly selected person has their money with either a finance company or a credit union? Well, it's going to be this plus this. And so we're going to use the addition rule. Now, since there's no overlap between these, okay, because we're assuming that one or the other, right? So there's no both. So either they're with this or with this, but not both, okay? So we're going to add these two probabilities together, and we get a 0.3339. right? So 0.3339 is the answer. Okay, now look at this one. Susan is a college student who receives heavy sweaters from her aunt at the first sign of weather. Susan has determined that the probability a sweater is the wrong size is 0.47, close to 50-50. The probability that it is a loud color is 0.59, so it's a little higher probability of being loud than it is that it's the wrong size. Okay, and the probability that it is both the wrong size and a loud color is 0.31. So A says find the probability that the sweater is the correct size and not a loud color. Okay, well, what's the probability that the sweater is the correct size and not a loud color? Well, guess what? We can use the Venn diagram to help us with this. Okay, so let's use a Venn diagram to help us answer these questions. So this is going to be the probability. So we're going to take, again, Venn diagrams are used in sets, but we can also use them for probability because we're going to take each of the numbers that fall in the sets and we're going to divide by the total number in the sample space. And if we do that, we get a Venn diagram that deals with probabilities. And so in this case here, we're going to say, hey, the probability that of being the wrong size is in here, so the number of items in here. So the probability that a sweater is the wrong size is what? 0.47, right? So we see that this number here and this number here adds to 0.7, right? Now we know that the probability, and how did we get this? Well, we know that the probability of wrong size is 0.47. And we know the probability of being loud, a loud color, is 0.59. Okay. But we also were given the probability that they're both the wrong size and a loud color is 0.391. Remember, we always start with the intersection. So this is the intersection. So that means the 0.47 minus this will give us 0.16. And the 0.59 minus 0.31 gives us this. So now we got these pieces. Now, the whole thing has to add up to 1, which means we add this region, this region, this region, and this region has to add up to 1. Well, these three add up to 0.75, which means the probability of being outside both of these is 0.25. Okay, so now we've got our Venn diagram set up, and now we can go back and answer these questions. So find the probability that the sweater is the correct size and not a loud color. The correct size, well, where's the correct size? The correct size is outside W. Okay, so outside W is everything here, right? So we want the probability sweater is the correct size and not a loud color. So the correct size and not, so we're outside this circle and we're outside this circle. So the correct size and not a loud color. So that means we're in the white here. So that means the probability is 0.25. Okay, the probability that a randomly selected gift, a randomly selected sweater that was sent to her is both the correct size and not a loud color. That's going to be 1/4 of the time, 0.25. Okay. Now, what about the second one? Find the probability that the sweater is the correct size or is not loud. Is the correct size or not loud. Okay. Is the correct size, so what's the correct size? The correct size is what? Outside this. What's the probability of being the correct size? That's 0.53. Okay. Okay, what's the probability of not loud? The probability of not loud is what? Well, it's going to be the complement of this one, which was 0.59. So it's going to be 0.59. So it's going to be 0.61. Okay, so the probability of being the correct size is 0.53, and the probability of not being loud is 0.61. So let's add those together. So 0.59 plus 0.61 is what? 1. Okay, now don't jump the gun, right? So the probability of a sweater is correct size or not loud. So again, it's going to be the probability of the correct size, which is 0.53, the probability of not being a loud color, which is 0.61, but we also have to subtract off the intersection of those two, right? What's the probability of being both? Well, we got that in the first part, 0.25, right? Because we're counting this twice, okay? Because outside here, right, the outside of this circle is 0.57, or excuse me, 0.53, because now it's outside the circle is 0.53, but that also includes this 0.25. And being outside this circle is 0.61, but that also includes this 0.25. So we're counting this 0.25 twice. So we're going to subtract off the 0.25. So the total is going to be 0.75. And that's going to be our answer. Okay, and that ends this section, section 5.7.4. So next time, we're going to talk about something which is a really cool thing called conditional probability. And we're also going to talk about the independent events. And we'll talk about something called the multiplication rule. So we've talked about the addition rule. The addition rule has two things. There's if the general addition rule and the simplified addition rule. The general addition rule is the one where you have to subtract off the intersection. The simplified addition rule is where you don't have to subtract off the intersection because they're disjoint events, and so the probability of them happening at the same time is 0. Okay. So now next time we'll talk about conditional probability, independent events, and the multiplication rules. Okay, or the intersection rules, I think is what they call it. I'm not sure. But anyway, make sure you do the examples. Make sure you practice. Do the guided notes. Write down your questions. If you get stuck on something, bring it to class so we can work on it. Until then, have a great day.